We now reach section 13.3, where we embed Cartesian motion planners in action servers. So here our goal is to have robot agnostic, high-level action clients that can generate robot trajectories. That is, we don't want our action client to worry about what robot we're using. We just want to give it a plan or an execution and then get the robot to move, any robot to move. So here in our Cartesian Planner package, we're going to have clients that are generic, but we're going to have action servers that are robot specific. So as we've been presenting earlier, we have, for example, a 7 degree of freedom action server, Cartesian mover action server. We have the Baxter right arm Cartesian mover action server, and we have the UR10. Let me show you just real quick. If I say raw CD Cartesian planner and go into source, we're going to see a lot of files here. Actually, let me show them like this. But you'll see that right here we have the action server for the 7DOF. Here we have the one for UR10. Here we have the one for Baxter. The rest of these files that are called example are the ones that are going to basically do the high level calling. And I'll show you those in a second. Now, in order for our client to be generic, we need an action message that is also going to be generic. So we define this message called the Cartesian move action message. I'll show it to you in detail in a second, but one thing I want to emphasize, for example, is that here as part of our goal, one thing that we want to send is a command code. This is represented as an integer, and we're going to create some macros to say what kind of command do I want to send. Do I want to plan, or do I want to execute? Do I want it to be a joint space trajectory, or do I want it to be a task space trajectory? After you provide the command, you may want to have a desired post gripper or not, or you may want to have an arm displacement. This would be a 3D vector displacement relative to the current post, so just move forward some distance or move up some distance. Or you may want to have the joint configuration goal, and then this might be time scale stretch factor, where you make the trajectory slower or faster. Let's take a look at that message. So if I go up here, we find our action folder. We have our Cartesian move.action message. And so here we're going to find our command modes. We have a bunch of them. So here's, for example, this section right here is requesting for motion plans. So this is just, if I want just to plan but not execute, then I should use a command code like this. Plan a path from current to waiting pose. Or plan a joint space path from the current location to a Cartesian gripper pose. Or plan path current to goal gripper pose. And so on. So you'll find all the different possibilities right here. After that, if we want to execute, we have this command code, execute planned path. Okay, so all of those, we need to choose one for our command code right here, and then our different goals right here. In terms of our result, we can get a number of events. Success would be 0, or ARM received and initiated request 1, ARM request rejected, already busy 2, and this list can be as detailed as you want it to be. Command code not recognized 8, etc., etc. You can get the error code here, the error message here, computer arrival time here, and then at the end some optional feedback if you so desire. Okay, so here's a summary of these things. And so we have the desired post gripper and the arm displacement. So let's take a look at how do we use all this. We're going to start with the main calling code called example generic move action client. Let's take some time to look at this diagram and try to understand what's happening. So over here we have the example generic Cartesian action client. What we're going to do here is we're going to instantiate an object of the arm motion commander class. This arm motion commander class is actually the generic path planning action client. And so what we're going to do right here on this side is we're going to say, hey, number 1, I want to plan something. Number 2, I want to execute something. And then number 3, I want to get some pose. Now notice that here we don't have to worry about creating the action client, and we don't have to worry about connecting to the server, checking for the connection, and dealing with callbacks. We just say plan, execute, get pose. Over here we have the actual client. And so what we're doing is we're encapsulating the routines for path planning. Here in the client, we're going to have different options for path planning and different options for execution. So here is actually where we set the command mode and then with the appropriate starting and ending angles. This class is defined by these two files, Cartesian motion commander.cpp and .h. So here the client encapsulates our plans and our calls to execute, and they go into a robot-specific planner action server. Okay, so these servers that are robot-specific are what are doing the low-level things that we discussed in section 13.1. So maybe we want to plan a joint trajectory. So this one will sample appropriately, we'll call the right inverse kinematic solver, and then we'll also do the optimization of the joint configuration sequences. Okay. It returns the result of the computations to the client, and eventually passes this to a joint trajectory client, as we saw in the previous lecture. And so then this joint trajectory client is getting, say, the 60 points that we sampled in our previous example, and sending them to the robot joint trajectory action server, which actually gets to move the robot itself. So this is a new level of programming in the course, because we're abstracting a layer of RAWs through a higher level API, which is very useful. It reduces tedium because we just very easily just call what we need, and the lower level class will take care of it. Another interesting thing that we're doing here is that we have an action server that is implementing, an action client within it. And so this server also has a client that sends goals out. So this is also new here. So having said that, some of the examples of actions that we have might allow us to have a straight line Cartesian plan or a curved trajectory coming from a joint plan. So let's look at this file first. And I have previously opened them here. Okay, so here we have the example generic Cartesian moving AC. So this is the high-level callable function. And so here we have a simple action client. We have the Cartesian planner message, and also the class for the header file of the class that we're gonna call. Here in main, we instantiate the class right here, arm motion commander, and this is what's gonna let us do a lot of the high-level operations. We have some transformations, utility functions that we want to do. And so here in arm motion commander, we might say something like, let's move to a waiting pose that is hard-coded, so just plan to move to a waiting pose. Maybe you could see this in RViz. If you like it, then you can execute the planned path. This function, execute planned path, assumes that we already have a optimized plan. And so at the end of that, you could request for the joint configuration data. We could also request for the tool pose, and we could also get the joint angles. Here, for example, we might have a slightly different motion. Just we might want to modify the joint angles by some small amount, so it's a displacement, and then we can call plan a joint space path current to Q goal. And so you plan for that, you pass in the joint angles, and then you get an optimized trajectory that you can visualize and then execute when you wish. And again, you can request the data. So if we go into any of these functions like plan JSpace, here we're just calling. So you can see that the whole main file here is high level and easy to use. Here at the end, after trying some of these things, we have a while loop where we do just a basic displacement, and this would be plan path current to goal displacement XYZ, and then execute it. So this is what this looks like. And so you can see the encapsulation. It's good to avoid the code tedium, and it's going to implement this class over here for easy programming. Now let's go ahead and look at our arm motion commander class that's doing the encapsulation. In this class, we'll see that basically in all of these things, we're going to first populate the goal message. Where do we want to go? And then we'll have command codes to request for a plan to the desired motion. Then we have command codes for the execution. And of course, we're always returning a response from the callback function. So we can look at both the header and the CPP file. Okay, I should have this open here. And let's start with the header file down here. Okay, zoom in some. And so here we have our class, arm motion commander. We have the action message goal. So it's Cartesian move action message, but this is the goal. We have the result. So we're going to be returning those. Something to hold the pose of the tool. And this is, of course, a client. The type of our client, action client, is Cartesian planner, Cartesian move action. So our message defines our interface, and we're going to instantiate with this name, Cartesian move action client. We have our callback when things are finished, where we're reading the result and the state. Okay, and so here we also have all these planning and execution techniques or approaches. So just as we saw in our callable main function, we can plan to move to a waiting pose, or we can plan to a path current to goal gripper. So all of these are going to be implemented here. Okay, these are public interfaces. So in our CPP, we see that in our constructor, the first thing that we do through the initialization syntax is assign an action topic to our client. So that's going to be Cartesian move action server. Okay, and then eventually we check for a connection, waiting for the server, and do the connection right there. And the done callback, we just return some basic information. So let's look at, say, some of these planning functions. Plan, path, current to go, gripper pose. And you can see that here what we're doing is setting the command code to the right thing, setting the desired pose, and then for this particular plan, we're ready to send the goal. So we do that, we send our message, we send the callback, which is the done callback with 2 arguments, and then we're ready to receive the result here in Cartesian result. And here we're analyzing whether this did not finish, the path was not valid, or actually we got some success over here. We can also look for not just the planning but the execution function. So it's this one right here, execute plan path. And so here the only thing that we're changing is our command code now is for execute plan path. We have the same goal as before, nothing changes, and then we have the same feedback. So this is a very nice high-level interaction with our server. Okay, we don't, in terms of the client, we don't need to be aware of what robot is running, Baxter, UR10, 7DOF. We're just focused on moving the tool in the relevant space, and all the inverse kinematic solving and planning is done on the action server. One thing we need to pay notice is related to frame names. Different robots will have different names for the base and also for the endpoint or for the tool. For example, the Baxter robot has its base frame, the frames called base and right gripper, but the UR robot has the frames called base link and tool 0. So these names may vary across robots. How can we generalize then the name of these frames to facilitate generic code across robots? The solution for us lies in using static transformations in our launch files. We've used static transforms in our course before, and so in this launch file, the way we try to generalize this problem is by taking a static transformation and saying, let's take the base name of Baxter, which is actually torso, not base. I made a mistake earlier. It's called torso, and then rename it as a system reference frame. and you might have a transformation here. This negative 0.91 in the XYZ direction means that you want to make the system reference frame go from kind of like the belly button of Baxter or the torso all the way down to the floor. So this is measured with respect to the floor. And then the right gripper frame, which is in the middle of the fingers for Baxter, will be renamed to be called generic gripper frame. Okay, and for the UR10, we might have a frame called world, and then rename it system reference frame, and then tool 0 generic gripper frame. Okay, and so here there's now in terms of the action server, we're gonna look in detail how this works. Now look at what we studied before. We have this robot specific planner action server. Let's take a look at the UR10 for example, and we're getting the requests or the goals from our client in terms of what we want to plan or what we want to execute. So we're going to look at the interface and the way that we plan and the way that we call the execution. We'll also see that, interestingly enough, we're going to call or create a client for a joint trajectories action that will in turn be sending these trajectories out to a server, which can move the robot arm out. Okay, so let's take a look at that code right here. So this is UR10 Cartesian move action server, and this is a pretty large file. There's a lot to learn here. Here is our Cartesian move action message definition. Okay, here we have a planner header file for our planning class. Here we have, this is both an action server, but it also has the action client definition for the trajectories. We have the joint trajectory message definitions. We have the kinematics as well. We have a bunch of ROS message types, a few utility functions, and of course many global variables here that are going to be used for all kinds of things. Because this is robot specific for the UR10, we define the 6 joint names right here: shoulder pan, shoulder lift, elbow joint, and then 3 wrist vectors. Let me quickly move to the constructor. Okay, so here we have the arm motion interface constructor. We're creating our action server object here using this action topic as before, and you'll see that the main callback function for this is called execute callback. Here we're also creating our action client called arm controller follow joint trajectory. Okay, and here we have some pre-poses that we might use. And here in the constructor, just doing a test mode where we're gonna check see if things are working right. We have our TF transform listener object dynamically allocated. That's going to help us to do a lookup transformation from generic gripper frame to tool. Okay, and just get some initial information. Utility functions to print our transformations. And then here, the joint trajectory action client is also going to try to connect and start the action server. So there's a lot of information going on here. You'll need to take time as part of your homework to sift through all of this and try to organize it. But remember just this diagram right here. That's going to help you just keep everything in check. Now let's look at execute callback. So in the execute callback, we see that we receive this goal, and immediately that goal is copied over right here into Cartesian goal. We also extract the command mode from it, and then we do a switch statement based on the command mode. So we might do a test, we might do some planning, and we have several cases for this. Plan joint space, plan, some time rescaling, and then here we actually have the execute plan path. And that's in terms of this case, which can call the executed plan move function. And for all of these other ones, we have specific planning functions. So of course we can go into these planning functions and then see what they do. So for this one, for example, any of these, let's try this one. We might find this planning function right here with our Q start and our Q goal coming in. And this basically calls another path planner with the start, with the goal, and then returning the optimal path. And then this stuff trajectory function is what gets the optimal path and copies into the desired trajectory. And then we're getting times here, computing arrival times, and and then doing some other calling here for let's see, maybe the stuff trajectory is also making the call here, and then just extracting some of the results like the time, the arrival time, and then if the path is valid, set as succeeded. So this takes care of all the path planning, including the inverse kinematics, and then you do the execution a little bit later. I think that's execute planned move. See, so here, if the path is valid, we send the goal to the action client with this goal right here, and a done callback over here. So basically you can look at the details in your homework, but this is how the action server is working. And so here I just summarize the beginning of the execute callback function, the planning, and the execution. Great. So now we're ready to actually see how this might work. We're going to use the UR10 robot to give the example. So to use the UR robot, we use the UR gazebo package to launch. We're going to use the UR10.launch package to get it started, getting gazebo running, and get all the controllers loaded up. And then we're going to do the static transforms launch file to have the appropriate frames of references. So down here, I can start UR gazebo. Do the static transforms. If you want, you can do a TF view frames to look at all those transformations here. Then we want to run the action server for UR10. That's the code we just reviewed. So here we're ready to start servicing Cartesian space scopes. And what we're going to do here, sorry, now is run the action client. And this is going to do a few routines. And at the end, we're going to be able to input a desired delta Z at the prompt. Let's then take a look at our UR arms. So you can see some of the different motions that we had in that file, and then coming here at the end on a while loop to enter some delta z's. So this delta z's will just displace the tool by whatever amount we enter. The range is from negative 0.5 to 0.4. So here, for example, if we want to move the hand down, I might just enter that displacement, and we can see that got response in time, returned success from the planning request, computed the move time and this much time, and then we request the execution of the planned path. We got a success here, and you can see that the response is very fast. So all of this is making use of our action client and then server, and then passing that to the joint trajectory server in turn. We can also go up at a different rate, like this, or go down in larger increments. Yeah, there's some displacement in this direction and some displacement in this direction, but you can see that we have a very smooth interaction between our servers and our clients. This is just a summary of that for you to look at home. So I hope this was an interesting section for you, combining all of the techniques into ROS action servers to get a motion planner running. As part of your homework, you're gonna get to test some of this with test motion planners with MoveIt, which of course is popular and de facto standard motion planner, but the goal of our lesson here has been for you to have a deeper understanding of how motion planning looks behind the scenes in a very elementary way, but still a very good introduction into motion planning. See you in the next section.